I welcome you all, and we are going to discuss today about the finite element method of analysis in structural analysis, right? So basically, this is how you mathematically formulate and mathematically discretize any structure into simplified form, right? So that means you cannot solve each and every structure around the world using finite element method manually, right? You need a higher computational power because if you have a bar element, right? So this is the simplest mathematical model with two nodes, right? You can solve this if you know the displacement of this portion and this portion. But let me say it's like some tower, right? So you need to discretize in several nodes. That means you need more number of finite points to solve this. So that means you need to solve whatever the forces or stresses, right? So that means you need to know at least some points, right? What happens if you have only 2 points? This is no way giving you the correct results. But what happens if you increase the points? You need to determine the stresses on this area. So if you increasing the number of points you have, number of known displacement or whatever, right? That means this will give you more generalized function. That means that can interpolate between these and give you some approximate solution. What happens if you actually define some nodes at each of these points where a significant change can be expected? That means this is becoming more closer to the actual solution. And if but with the displacement, the now this shows you how much equation you have to solve, right? Here you have two equations. Accuracy increases as well as the computational power, right? That means you can't solve these things manually, right? So maximum you will have, and simplified cases you can solve using finite element method in your civil engineering degree related, right? So we will go with the basics and we will recall the structural analysis, solid mechanics, and these things, right? And the first thing is, so we can determine what is the stress at a point, if it is 2D or 3D, right? So if it is 2D, you have several stress component, normal stresses and shear stresses, right? If it is 3D, you have 3 normal stresses and 6 shear stresses, but these two are, these couples are equal with each other. That means this becomes 3, right? If this is equal, this is one unknown, this is another unknown, this is another unknown. So that means altogether 3 unknowns and 3 normal stresses. So that means you have 6 unknowns. Here you have these two equal. So that means 3 unknowns. Why? 1, 2, and 3. Right? This is just the representation of a stress at a point when a load is applied, right? And this is how you write it, right? So this is a symmetric tensor, right? And these two are equal. And if it is 3D, you know, 9 components are there, but already 6 are there. Couple of them are so equal with each other. So for instance, this is equal with sigma yx, and this equal to sigma xz, and this is equal to sigma yz, right? So altogether you have 1, 2, 3, 4, 5, 6 unknowns, right? So this is just a representation of the forces per unit area, right? Shear stresses and normal stresses. And if you call the strain, right? So the simplest fundamental meaning of strain is the elongation per the original length, right? That's it. So just consider a bar element. If you apply a force, let's say there's a displacement of delta, the initial length was L, so the strain is delta over L, right? So this is for a 1D case, right? But if it is 2D, you can't write a simple equation as it is, right? So there will be different components, sigma xx, sigma yy, and sigma z. So these are normal strain and these are shear strain, right? So u means the displacement in x direction, v means the displacement in y direction, and z, I don't know why is it, yes, y, and in the z direction displacement is w, okay, for a 3D case. And this gives you daba partial derivative of v with respect to daba x. So this really tells you how the strain relate with the displacement, right? How the shear strain relates with the displacement. So in the end, you are giving you are obtained how the strain relates with the displacement or displacements, the relationship between them, right? That's it. So this is telling you if you differentiate u with respect to x, you will get the strain in normal direction of x, right? Okay, so it's again a symmetric matrix, right? So in Hooke's law, so for a 1D case, you are giving a P force axially, right? So you know this is stress and strain, right? Okay, so this law. When there's a region where your stress and strain increases linearly, we call it elastic region, right? Beyond that point, you have larger strains even for a constant stress, right? So that means it is non-linear, right? Not linear. That's it, right? This is the linear region. So in this finite element course, we will be basically dealing in linear finite elements, right? So these are for linear elastic behavior, right? That's it. That is the simplified assumption of this, right? And if you have something like this, you know, for a 1D case, you can just write sigma is E epsilon naught, right? But for a 2D case, so you remember you have 3 different sigmas, and here you have 6 different sigmas. So you can't directly write is equal to E epsilon naught. There are some matrix combination, right? So that is becoming with higher dimensions. So sigma becomes some matrix, we don't know what is it, still into the strain, right? There will be 6 strains as well, right? For a 1D case, this is straight away becomes E, right? But this D actually, this 1D, okay? But this D actually, this is a generalized Hooke's law, right? Generalized Hooke's law. So this D matrix, right, depends on actually E, Poisson's ratio, and the material properties, right? Material properties. And I'm repeating, this is generalized Hooke's law for 1D, 2D, or higher dimensional element. And if it becomes 1D, you can write this stress, because in 1D element, you have only one stress component and one strain. That's axial, right? So this is straight away becoming E. Sigma equals to E epsilon naught. And yes, one thing is, and the strain energy, it's some kind of potential energy. I'm recalling this potential energy stored in the element due to the strain, right? So we have done the energy method also. Castigliano's second theorem and first theorem, they tells you like something like this, right? So the second theorem tells you partial derivative of total internal energy. So we write it as U with respect to force applied at any point is equal to the deflection at that point, application of the force of the direction of the line along that force, right? That's simply telling you if you differentiate, partially differentiate the strain energy with respect to the force applied at that point, it gives you the displacement along that direction, right? This is the second theorem. And if you interchange this, du over dd, it's a Castigliano's first theorem. If you differentiate, partially differentiate the strain energy by correspond to the displacement partial derivative, that gives you the force along that direction, right? So these are the theorems in energy methods, right? And then you can write this as, so this strain energy, you can, this is the elastic region, so the area of this, so you have learned it in your high schools as well, right? So the total strain energy can be written, so let's call it, so this is 1D element, right? 1D element, and it's giving the area, right? Sigma into epsilon naught into, let's call it d omega, and this is the energy density, right? This term will give you the energy density. So you need to determine what's the total strain energy, right? That so if you if you integrate this over this area, so that will give you the area of this triangle, that is half into sigma epsilon naught. So you need to again integrate this over the total volume to get the total strain energy, right? So if you want, you can take this half out. Okay, that's a constant. And yes. So the next thing is, we know that from the matrix method of analysis, we choose displacement method, right? Not the force method, because displacement method is more convenient. You know the displacement, you solve for that, and then determine the forces, right? So in the displacement method, we solve for equilibrium, and we know that there you have force is equal to stiffness times equals k into x, right? So the simplest form, force is equal to, so we write this in this form in the matrix method of structural analysis. Stiffness into displacement, right? So you have now several relationship that's called sigma is equal to P into epsilon naught. This is a generalized Hooke's law. So this simply gives you how the strain related with stress, right? Stress is some matrix into strain, right? For a 1D case, this is straight away becomes a linear equation like sigma equals E epsilon naught. Okay. And for this epsilon naught, so you saw that earlier. Epsilon naught, let's say you remember epsilon naught xy, was there something like daba u daba v over daba x plus daba u over daba y, likewise some sort of things like that. So you can write this as a matrix form, daba x daba y into v and u. So this thing you can call B, some matrix, right? This is what? The displacement, right? So you can write this as B into the displacement, right? And the strain energy, you remember, you take the half out, the volume integral of sigma into epsilon naught dv, right? So sigma is d epsilon naught, right? So these things are in matrix form, right? Either you should take so you can't write as multiply as it is. Most of the times if a matrix like this, you have to, if a matrix like this 1 2 3 1 2 3, you can't multiply it like this. You need to transform some matrix, that means like this at least, right, to multiply with this, okay, or like this, whatever. So I'm transforming the epsilon naught matrix so that I can write sigma is equal to B into D, okay. And you can write this as B D epsilon naught. So this epsilon naught you can again write as B into D, right? This. So I'll erase this epsilon naught and write it as B into D. Right. So here is U, and you and me know at Castigliano's theorems, daba U over daba T is equal to the force, right? Remember the first theorem? So what happens if I differentiate it partially? So there is d square term. When you differentiate it, 2 comes in front of the equation and it gets cancelled with these 2, and 1d is remaining, right? So you can write like this. To dv into d, right? So equals to f, and f is equal to k into, or s, you can write it as s, stiffness matrix, as here. Okay, you can write k. Okay, so this is this matrix, k into d. So you can see that an equation to k into d equals to f. So that means k should be this part, this into d, right? The same expression, right? You can write stiffness as volume integral matrix P transpose into d dt, right? This is a volume integral, right? So the size of this depends on the elements you choose, right? So for instance, if you have 1 degrees of freedom, 1 degrees of freedom, so you will only have, this is one linear equation, right? This is just one linear, not a matrix, one element in each matrix. So this becomes this, this becomes a scalar. This becomes a scalar. So if it is 1D, it straight away becomes Young's modulus, right? For 2D case, or 2 degrees of freedom, let's say, you will have 2 by 2 matrix, and then the matrix will come into play, right? If it becomes complex, it will become more complex, right? So degrees of freedom is 4, so this will be a 4 by 4 matrix, right? So then the things are getting complex, right? And we will go with the simplest element, right? 1D bar element. Okay, so for the examples as is, we can take this part. So we can define some non-displacement here likewise, right? Oh, we don't need that. We will check. Let's say we take an element like this. Let's call. So we know at here we know the displacement is 0, right, in axial direction, because a fixed support cannot displace. But we will take a general element like this. We will say this is at x equals x1, and this is at x equals x2, right? So we need the displacement in terms of, so we know the displacement at the ends, it's u1 and u2. Okay, so we only know 2 points. We need to know what will be the displacement in each point, if you say any point, right? So to in order to do that, we need some expression, but you only have 2 points, so that means you can only write a linear equation. If you have 3 nodes, right, you can write a quadratic equation like ax squared plus bx plus c, right? For this case, you can't have that. You only have these 2 equations, right? So these 2 displacements, so that you can write maximum the displacement in x direction can be written as ax plus b, right? Because it's a linear, because you only have 2 points and you can determine these 2 constant, right? At x equals x1, u1, u is actually u1 at x equals to x1. At x equals to x2, u2 becomes ax2 plus b, and we know that x2 minus x1 is equal to L, right? Yes, we can write this as so you need to find these coefficients, so you can straight away find a is equal to u1 minus u2 divided by x1 minus x2, and you can find b as what? u2 x1 minus u1 x2 over x1 minus x2. Right, this is very generalized expression, that's why I didn't do this x1 as 0, right? If it is 0, then let it be 0 then, okay? But then if you substitute these into a and b, you can write ux as, and I'm taking the u1 terms to closer, right? So you can write like this when you simplify it: x2 minus x over L into u1 plus x minus x1 over L into u2, right? So for this case, you can write this n1 1 plus, for this you can write this part as n2. These are called shape functions, okay? These are called shape functions. So the displacement, so let me show you what are these shape functions are actually. So n1, right? So n1, you remember, n1 is x2 minus x over L. And if you can draw a graph for that n1, right? And n2 is x minus x1 over L. At x equals x1, right? At x equals x1, so this n1 becomes this n1 becomes what? N1 becomes, so x2 minus x1 over L. So you know that x2 minus x1 is L, right? So this becomes 1, right? At x is equal to x2, this becomes 0, right? So that those are the only points you know. So you can draw like this. At x equals to x1, this becomes 0, and x is becoming x2. X2 minus x1 is L. L over L is 1. This one side is 1, right? Okay. So these are the shape function. Okay. So this really means an important thing that called, so your u is n1 into n1 into u1 plus into u2, right? So let's check. This is a rigid body, this element, right? This is rigid body moving in x direction. So if it is a rigid body moving, so you know u1 is equal to u2, and whatever displacement in this, it's like a car moving on a highway, right? So that headlight, if the headlight moves 1 meter in the direction, tail light also move one meter, and the person who's sitting in the driving seat or any other point will move exactly 1 meter. So that means u1 equals to u2, and any displacement at any point becomes u, right? So if it is rigid body, right, so your u1 is equal to u2 equals to, let's say, delta, right? We call it. So any displacement also going to be delta at any point, right? So n1 delta plus n2 delta, right? Delta is getting cancelled. This brings you an important theory, n1 plus n2 is equal to 1, right? At any point. So you can see 0 plus 1 equal to 1. So this is increasing, but the summation always 1, right? So you can write sigma n equal to 0, sorry, 1, right? So these are the shape functions, so that you can mathematically idealize it, right? So the thing is, if you want, you can get 3 elements like this is, right? So this is 2 node element. So you can see the linear function and the shape function like this. So the summation is like this, right? So u1 and u2. So if you take two nodes, right, 3 nodes like this, I think they are referring to this epsilon naught as the strain. So that means x over L, right? X over L. So they can write epsilon, right? And then you will have 3 equation and 3 shape functions. But whatever you can see, okay, these things, when these things are 0, this is 1, right? The summation of these 3 always shape function 1, right? So you will have some kind of displacement like this theoretical, right? And when it becomes 4 elements, so this is becoming computationally expensive, and in the meantime it is getting more realistic and accurate, right? So this is the beauty of finite element, that you can't solve this everything using manual methods, right? But you have to use some programming or calculation. That's what software does to you. You only need to understand the basic concepts, what's happening inside these programs, right? So let me go with the bar element again, and you can define a bar element. So for the bar element, you know, only you have the strain in axial direction, right? So your strain, you can simply write da by u over da by x, right? Where did I get that? You remember this? This is for a 2D or 3D somewhere. So we only have one strain component. Why? We are working in 1D problem, but it's only things are happening in this longitudinal direction, right? It's like a truss member, right? So du over dx. So this u is what? The displacement, not the strain energy. This is displacement. So there are several u's, so don't be confused with that. This is displacement, okay? So the displacement function you found as what? N1 into U1 plus N2 into U2, right? So this is going to be strain DABA N1 U1 plus 2 U2, right? So this n is a function of x, right? So this x2 is a constant, x1 is a constant at some point. It's a some point, right? Those are some points. X is the variable, right? So this is just like a constant. So you can just differentiate it here. DABA n over DABA x becomes, you can separate this as x2 minus L minus x over L. So this is a constant, totally constant, so that the differentiation is 0. And this is x over L, x to the power, so x into some constant, right? So your differentiation gives you 1 over L, right? 1 over L, and this will give you plus 1 over L, right? So you can write this as, so you can write this as matrix form. DABA n, DABA x. So this U1 is a constant, right? U1 is a constant. You can write this as matrix form DABA into, wait a minute till I write everything. Into U1, U2. So when you multiply it, this will be multiplied by this will be multiplied by this, right? So this is 1 into 2 matrix. This is 2 into 1 matrix, right? And this is epsilon naught, right? So this we can call B. So you saw DABA n over DABA x is what? Minus 1 over L, and this is plus 1 over L, right? So you can easily write this as minus 1 over L, and this is 1 over L into the displacement matrix, right? U. U is this U1 and U2, right? And you know, sigma is E into epsilon naught. Now we are in 1D state, right? So you can simply write this as simplified form of E into epsilon naught, right? What is epsilon naught actually? you know the epsilon naught, right? So you can write the stiffness as the volume integral B into D into P dV. So the dV is, so this is a bar element. So if we take a small element, it will be like this, right? So this is area of A, and this length is dx. So we can write dV as A into dx, because your area does not change with the length, right? If your area is like this, it's a tapered beam, even if you can write some function to represent A, or else there are several methods to simply idealize that, right? That will be discussed later in the example. And you can write this. So we know the D is straight away E, okay? So we know B is 1 over L minus 1 over L, right? So if you take 1 over L out, so this is the transpose, this is minus 1 plus 1. This is E, right? So this is going to be again B matrix minus L into A dx, right? So you can take A E over L squared out, and you will be remaining with this matrix 2 into 1 plus 1 into 2. So that will give you 1 minus 1 into dx, right? So this is dV, but we know the area is now constant, so this is become a linear integral over the entire length, right? So dx means this is just x, right? X is from 0 to L, right? So that becomes L. That L is cancelled out with this L, right? This will be an L, this will be cancelled. So your stiffness matrix for a bar element with 2 nodes will be like this. Simple as it is. Okay. So we shall, so this will be the components of, so this is U1 at first node, this is U2, this is again U1, and this is U2, right? Okay. We will consider an example from this.